Hello and welcome to Prepspot. In this video we are going to know about some groundbreaking news from the field of astronomy, a discovery that has captivated the scientific community and is reshaping our understanding of planetary systems beyond our own solar system. On 11th March 2025, astronomers announced the discovery of 4 small, rocky exoplanets orbiting Bernard's star, a red dwarf located approximately 6 light-years from Earth. This news, published in the astrophysical journal Letters, represents a significant milestone in exoplanet research because, while these planets share a key characteristic with Earth, their rocky, terrestrial composition, their distinct differences in size, mass, orbital behavior, and environmental conditions set them apart as fascinating objects of study. Bernard's star has long been an object of interest for astronomers due to its proximity and high proper motion. Its status as one of the closest stars to our solar system makes it an ideal candidate for exoplanet detection efforts. The discovery of these planets builds on decades of research using advanced observational techniques, particularly the radial velocity method, which detects subtle wobbles in a star's motion caused by the gravitational pull of orbiting planets. In this case, astronomers employed state-of-the-art instruments such as Merunex, located on the Gemini North Telescope in Hawaii, and Espresso on the Very Large Telescope in Chile. Over the course of more than 100 nights of observation spanning 3 years, these instruments captured the minute shifts in Bernard's star that indicated the presence of these 4 exoplanets. The research team, led by Ritvik Basant from the University of Chicago with contributions from colleagues including Jacob Bean, utilized the radial velocity method to pinpoint the planetary signals amidst the noise of stellar activity. Unlike the transit method, which relies on observing a planet as it passes in front of its host star and temporarily dims the star's light, the radial velocity technique allowed the team to detect the gravitational tug of these planets even though no transits were observed. This is particularly noteworthy because the viewing angle of the Bernard's star system did not favor transit observations, thereby making the discovery even more challenging and emphasizing the power of modern spectroscopy in exoplanet detection. In discussing these planets, it is essential to understand some key terminologies. An exoplanet, by definition, is any planet that orbits a star outside our solar system. In this instance, the 4 newly discovered bodies are particularly intriguing because they are classified as rocky planets. Rocky planets are those that have a solid surface composed primarily of silicate rocks or metals, much like Earth, as opposed to being composed predominantly of gas. However, despite this similarity in composition, the planets around Bernard's star differ considerably in several critical ways. They are much smaller than Earth, measuring only about 20–30% of its size, and their masses are estimated to be around 4 times that of Mercury. Their close-in orbits, with periods ranging from just a few days up to about a week, expose them to high temperatures due to their proximity to Bernard's star. These conditions make them inhospitable by Earth standards, especially when considering the requirements for habitability that include moderate temperatures and a stable atmosphere. Bernard's star itself is an intriguing subject. As a red dwarf, it is considerably smaller and cooler than our Sun, with a mass of roughly 16% that of the Sun and an age that is estimated to range between 7 and 12 billion years. Its relative closeness at approximately 5.97 light-years away not only makes it an accessible target for detailed studies but also provides an excellent laboratory for understanding the diversity of planetary systems around stars that are very common in our galaxy. Red dwarfs are known to be the most abundant type of star in the Milky Way, and studying their planetary systems is crucial for developing a more comprehensive picture of how planets form and evolve in environments that differ markedly from our own solar system. The discovery of these 4 exoplanets is particularly significant in the context of recent advances in astronomical instrumentation and data analysis techniques. Since the early discoveries of exoplanets such as Proxima Centauri b, which demonstrated that Earth-sized bodies could orbit other stars, the field has rapidly evolved. With the advent of the James Webb Space Telescope and improvements in ground-based spectroscopy, researchers have gained unprecedented sensitivity in detecting even the smallest wobbles of stars. This progress has not only increased the number of known exoplanets, currently numbering in the thousands, but also refined our understanding of the variety of planetary types that exist, especially those that are rocky and potentially similar in composition to Earth. Yet, while the similarity in composition may evoke comparisons to our home planet, it is crucial to highlight the differences that set these new exoplanets apart. Their diminutive size compared to Earth, coupled with their high temperatures and the likelihood of thin atmospheres, suggests that these bodies are not candidates for life as we know it. The high thermal environment, a direct result of their tight orbits around a relatively dim but active red dwarf, means that any atmosphere they might have is likely to be tenuous and subject to significant stellar radiation. This scenario contrasts sharply with the conditions on Earth, where a robust atmosphere and a temperate climate have been essential to the development and sustenance of life. In the case of Bernard's star's planets, their physical and orbital characteristics provide astronomers with a unique opportunity to study the extremes of planetary formation and evolution in close stellar environments. One of the most interesting aspects of this discovery is the implication that small, rocky planets may be more common around red dwarf stars than previously thought. Red dwarfs, due to their abundance in the galaxy, could potentially host a vast number of these worlds. Although many of these planets might not be habitable in the traditional sense due to their high temperatures and rapid orbits, they offer critical insights into the processes that lead to planet formation. Understanding these processes is essential not only for predicting where habitable worlds might exist but also for comprehending the broader diversity of planetary systems that the galaxy harbors. From a technological perspective, the success of the radial velocity method in detecting such small and close-in planets underscores the advancements in astronomical instrumentation over the past few decades. Instruments like MERUNEX and ESPRESSO have been at the forefront of this progress, pushing the boundaries of what is detectable from Earth. Their ability to measure stellar wobbles with extreme precision has opened up new avenues for discovering planets that might have been missed by earlier surveys. This breakthrough is a testament to the continuous improvements in telescope technology, data processing, and observational strategies that are essential for probing the subtle signals emanating from nearby stars. Looking toward the future, the discovery of these 4 exoplanets raises exciting prospects for upcoming missions and research projects. Although these particular planets are unlikely to be habitable, their proximity to Earth makes them prime targets for follow-up observations using both ground-based observatories and space telescopes. Future missions could aim to characterize their atmospheres, surface compositions, and even their magnetic fields, offering further insights into the physical processes that govern planetary systems around red dwarfs. Moreover, the techniques honed through this research could be applied to other nearby stars, potentially leading to the identification of more exoplanets that might fall within the habitable zones of their host stars. It is also important to consider the broader implications of this discovery within the realm of education and competitive examinations. For students studying science and technology, this breakthrough provides a vivid example of how advancements in instrumentation and methodology can lead to new discoveries that challenge our preconceived notions about the universe. The details surrounding the discovery, from the application of the radial velocity method to the interpretation of the planetary characteristics, are not only of interest to professional astronomers but also serve as valuable learning material for those preparing for examinations in astronomy, physics, and related fields. The significance of Barnard's star as a nearby laboratory for studying exoplanets makes this discovery particularly relevant, as it encapsulates key concepts in modern astrophysics, such as stellar evolution, planetary formation, and the technological innovations that drive scientific progress. As we delve deeper into the specifics of the discovery, it is essential to appreciate the careful planning and execution that characterized the observational campaign. The research team meticulously gathered data over an extended period, ensuring that the measurements were robust enough to detect the faint signals produced by the orbiting planets. The use of 2 complementary instruments provided a means to cross-verify the findings, enhancing the confidence in the results. This rigorous approach is a hallmark of contemporary scientific inquiry, where precision and reproducibility are paramount. The successful detection of these exoplanets not only reinforces the credibility of the methods employed but also sets a benchmark for future studies aimed at uncovering similar systems around other stars. Furthermore, the cultural and historical context of this discovery cannot be overstated. The search for planets beyond our solar system has long been fueled by a profound curiosity about our place in the universe. Since the early days of astronomy, scientists have sought to answer fundamental questions about the nature of celestial bodies and the potential for life elsewhere in the cosmos. The discovery of these rocky exoplanets around Barnard's star is a continuation of that quest, embodying the human drive to explore and understand the unknown. It builds on a legacy of research that stretches back to the mid-20th century and highlights the dynamic interplay between technological innovation and scientific discovery. In many ways, it serves as a reminder that the universe is far more diverse and complex than our limited experiences on Earth might suggest. In addition to its scientific implications, this discovery has practical ramifications for the future of space exploration. Although the newly discovered planets are unlikely to support life due to their harsh environmental conditions, their proximity to Earth presents a unique opportunity for testing and refining the technologies required for interstellar travel. Concepts such as nuclear fusion propulsion and light sail technology, once the stuff of science fiction, are now being seriously considered for missions that could one day explore nearby star systems. The insights gained from studying Barnard's star and its planets may, therefore, play a crucial role in shaping the next generation of space exploration initiatives, providing a tangible target for both robotic and, eventually, human missions. As we consider the scientific and technological aspects of this discovery, it is also worth discussing the broader impact on the field of exoplanet research. The discovery of these 4 rocky exoplanets reinforces the notion that our galaxy is teeming with planetary systems that exhibit an incredible variety of characteristics. While many of these worlds may be inhospitable, each one contributes to a more nuanced understanding of the processes that govern planet formation and evolution. The fact that such small and closely orbiting planets have been detected around a star as nearby as Barnard's star opens up new avenues of research, prompting scientists to re-examine existing models and consider alternative scenarios for how planets can form and sustain themselves in diverse environments. This, in turn, could lead to a re-evaluation of the criteria used to assess planetary habitability and spur further investigations into the complex interplay between a star's properties and the characteristics of its orbiting planets. For those of you preparing for examinations or seeking to expand your knowledge in the field of astronomy, this discovery is a treasure trove of information. It encapsulates fundamental concepts such as the radial velocity method, the importance of high-precision instrumentation, and the diversity of planetary systems in our galaxy. It also illustrates the iterative nature of scientific progress, where each new finding builds on previous research and opens up new questions for future study. Whether you are interested in the technical aspects of spectroscopic analysis or the broader implications for our understanding of the cosmos, the discovery of these 4 exoplanets offers a wealth of material to explore and analyze. As we draw this discussion to a close, it is important to reflect on the transformative impact that discoveries like this can have on our understanding of the universe. The identification of these 4 rocky exoplanets orbiting Barnard's star not only deepens our knowledge of planetary systems around red dwarfs but also serves as a testament to the ingenuity and perseverance of the scientific community. It challenges us to continually refine our methods and push the boundaries of what is possible, reminding us that the universe still holds many secrets waiting to be uncovered. While these planets may not offer a direct path to discovering extraterrestrial life, they provide a critical piece of the puzzle in our quest to understand the formation, evolution, and ultimate fate of planetary systems. In summary, today's announcement is more than just another headline. It is a significant leap forward in the ongoing exploration of our cosmic neighborhood. The discovery of these 4 small, rocky exoplanets around Bernard's star, achieved through precise and innovative observational techniques, underscores the dynamic and rapidly evolving nature of astronomical research. It highlights the importance of continuous technological advancement and rigorous scientific inquiry, while also inviting us to reconsider our place in a universe that is far more diverse and intriguing than we ever imagined. As we continue to push the frontiers of knowledge, discoveries like this not only enrich our scientific understanding but also inspire future generations of astronomers, engineers, and curious minds around the world. Answer this question in comments. The correct answer will be given heart and pinned. Lastly, we just want to let you know that we are a newly emerging online platform for competitive exams. Creating educational explainer videos like these requires a lot of effort, money, and time. If you like these videos and want us to excel and create videos in all categories of competitive exams, then you can consider supporting us with a one-time donation through the Ko-fi platform and also by becoming a member through Patreon. This will help us create more such informative educational videos in the competitive exams space. So, one last time, subscribe and share this channel with all your friends who are preparing for competitive exams. And also, follow us on social media platforms. The links are given in the About section of the channel and also in the video description. So, see you in the next video.